morning. Let's talk. Let's begin. And today we have a guest talk from Simon Lombakka from Elisa, telling about how machine learning will be used in the telecommunication area. So welcome and nice to have you here.
Thank you. Yes, so I guess the best people are the ones that show up today, because we want to see how things work in practice in the industry. I heard about your course. It sounds very interesting. I think it is very relevant to have right now a course in machine learning with some theory, some project that you need to program to actually make some machine learning projects. And it's kind of interesting that with these kind of current development in the science and in the hardware, you can actually do machine learning pretty much at home on your laptop, and you don't really need any supercomputer or anything like that. So that is kind of the interesting thing, and I guess there is a variation of people in this course. I heard it's like 900 or something registered, and maybe many of you have just heard the word machine learning. You don't know at all what that was before you started the course. Maybe some of you had already done some programming at home, and you have already done some neural network training and these things. So I guess it's quite big spread of variance in this group, and that is okay. In my lecture, we're going to go just on the practical side, what we do in Elisa with machine learning. This is going to be very hands-on, not much theory, not much kind of these deep insights into anything, but very, very practical hands-on. So machine learning in the industry, in Elisa especially, is very relevant right now. We are really pushing for machine learning. Since we're a telecommunications company, we have a lot of data. We have a lot of data we don't know how to process, and machine learning is pretty much the tool that we need to process, to progress in that field. So let's see at our use cases and what we have learned from using machine learning, and what is maybe useful for you to know what's going on in the industry. So we start with some key figures about Elisa. It is a growing company. Almost 2 billion in revenue, about 700,000 fixed broadband subscriptions. This was 2017. We primarily work in Finland and also in Estonia, and about 5,000 employees right now. So it's a big company. It's there in Pasila at the train station. You have probably seen the big antenna there on our roof of the building. And Elisa is currently the leading the market in Finland. 40% of the mobile subscriptions is handled by Elisa, and also the fixed network subscriptions. So it is an interesting company to work for, to be in the kind of leading role in this technology. And our job as Elisa is to provide internet connections to the people in Finland. And the most important thing for us as a company is to provide the user experience, to have the customer satisfaction, to provide the customer the internet connection wherever the customer is, with good connection speed, and it should always be available, no downtime and nothing like that. That is our goal, to make the customer happy, and that is how we keep our customers. We have coverage of 99% of 4G in Finland right now, so it's pretty much covered the whole Finland. Still expanding on gigabit speeds, and also we are pushing to be the leading leading provider for the 5G service in the future. So it is It's a lot of research. We actually push like 200 million euros in research every year, so it's a very active business in doing research. Now we also try to use more and more of machine learning, so that is the part where we need all of you to kind of take part into that really cutting edge research. I have one slide about machine learning as a whole, and it's not much. From our point of view, we have a lot of data, right? We have like really lots of data, because everything that the customer is doing, everything you do on the mobile phone goes through the Elisa network infrastructure. There's a lot of logging of that information. Some of the information is very secret, some is less sensitive, but all this information gives us some kind of ability to use to improve on that customer experience and kind of expand our customer base. So all of this data that we collect, can we use that for some good, for some kind of automation that would improve on the network capabilities? I work in automation in Elisa. It is a very quite close to the network level business unit, and there has been automation before. It's not only machine learning that gives us automation. We also have it before. This was kind of a traditional approach of doing automation. Very simple. For example, if you want to automate some kind of setting selection, right? So we have an if statement. If users is more than something, then select A. Else, if users is more than something else, then select B. So really simple kind of automation. And it works. It's okay. It's easy to program, as long as you have few variables. As long as you have very little input data. So in the past, we were looking on very few input variables, like number of users in a base station or something like that. And you can write your use case and your automation with few lines of code. But when the input data gets like 1,000 dimensions, it is out of the question. You cannot do that anymore. And if you want to update your code to optimize for something else, it is really a pain. So this traditional approach should be really just used for static automation cases. So now we want to ask the question, can we use instead machine learning to help us go deeper into this automation, to use more information to do automation? So the difference, as you maybe know right now, after taking this course, is that the logic, those all lines of if-then-else statements that was used in the past, that is not anymore what you use in machine learning. Instead, you use a model. You use a model that contains all the logic you need. But you don't write the model yourself. You train the model, so the computer actually makes the logic. And the model is more of a black box. You just throw in information to that model, and you get out what you train the model to actually do. So the interesting part in machine learning for our side is maybe the training and also the data selection. So how can you train the model to do what you want it to do? And can you train the model with sufficient speed? And can it be done in practice, so to say? In the academia, it's often more like you need the theoretical case to work. And usually when you start using machine learning and you download the tutorial examples, the data is super nice. It's like in a best format possibly, so you just need to basically press play and you have your model. But in practice, in the industry, the data is a mess because it's based on real measurements, and it's not very nice. So that part is maybe where it differs much from the industry and from the academia. You need to put a lot of effort on the data cleaning in the beginning. So this is the hardware we have. You probably have seen a lot of these antennas along the streets and on rooftops. So these are basically the endpoints that you connect your phone to, 4G, Nokia base stations, or Huawei base stations, or Ericsson base stations. And it works so that in this picture you have a lot of these base station sites. In one base station site you have many cells. One base station can contain, for example, 10 cells. And a cell is the thing you actually connect your mobile phone to. So you can have a cell with different bearings. They kind of throw the beam in different directions, use different frequencies, and so on. But that is kind of the hierarchy. So it's a base station, and in the base station there's a cell. And the cell, that is where you connect your mobile phone to. For example, if you have a connection to that cell right here on this base station, then you start to move your mobile phone more towards that cell, and at some point the signal quality to that cell here is higher, so then there will be a handover, then that cell will take over the connection from the other cell, right? That is kind of how it's solved when you move around your phone. Okay, inside this Nokia box, there's a lot of performance counters, right? A lot of performance counters. And these performance counters, they measure what's going on inside that cell. So when you do something on the internet with your phone, you download something, there will be a connection to that cell. You maybe start using the data, you fetch data from that cell. The performance counters start to register what's going on in that cell. And for us, we want to store all this data that the performance counter gives us, right? So here are just some examples of performance counters. They have these kind of weird names, but you have like thousands and thousands of counters that measure, for example, throughput, measure user activity, signal quality, all sorts of things that's going on in the base station. And you have, like, for example, every hour you have a data dump of the state of these counters. All those counters are stored to a big database with like many terabytes of data, just raw counter data. And what do we do with all those counters? So far we don't do much, or we haven't done much because we haven't used machine learning. But now when we have machine learning, we can start to use this massive amount of input data from these counters and to kind of optimize for certain cases. So this is the data we have been working on so far in automation. And all of my use cases are based on this kind of counter data that we have from these cells. So I have three use cases I want to show you. Three different problems that we want to solve: classification regressions and time series regression. At this point, I guess you know what this means. If you don't know, it doesn't matter so much because I'm going to show you what they are in practice. So let's just have a look at some use cases to see what's going on. Okay, the first use case is called alarm prediction. So for Elisa, as I said, the main thing is to provide customer satisfaction, and that means there should be no downtime in any of the base stations. When a base station goes down, you lose your signal to that. Then you can't connect to the internet anymore. Maybe some other cell from somewhere else kind of covers for that downed cell, but in practice you will get some you will get some problems in your internet connection. And if these problems are big enough, you start to call the customer center and say, my connection doesn't work, you are giving me bad service. And this is what we want to avoid. We want to avoid customers being pissed off, because that is how we lose customers. So base stations are, of course, based on hardware, and hardware will fail at some point. There is no perfect hardware, and it will fail sometime. But if we could predict when that hardware will fail, then we could prepare the maintenance crew beforehand and say, okay, this base station here, it looks weird. It's probably going down in 12 hours. So make your vehicle ready and go and check it out. Or maybe you can just do a base station reset if it's not so bad of a problem. So that is what we have done in Elisa, predict these failing base stations. So that is based on something called a base station alarm. And alarm is a flag that says, okay, some unit in this base station was now broken, and it doesn't work anymore, or it's about to go down. So we have some alarms that are not very critical, like you need a software update and something not very critical, but also we have these bad alarms that this antenna unit is really dead now. That is like one type of alarm. So we want to predict when will we have a bad alarm that will actually bring down the base station. And can we use all these performance counters to see, like, okay, if there's some pattern in these performance counters, maybe the throughput starts to go down even though it shouldn't do that, maybe the signal quality is going down or behaving weirdly in some way, then it might be a sign that, okay, now something is going to happen. That is the thing we want to do. So this is what we want to predict. I will explain the figure. This is time axis, and at some point in time we have a real base station alarm because some hardware was broken. Now we would like to predict in a 12-hour window in advance if that is going to happen. Because if we know that, then we can kind of prepare for it. And then we have plenty of time to kind of set up maintenance crew or do something else to prevent or minimize the downtime. So at any point in time, we would like to have some kind of algorithm that could, here it could predict, okay, will the base station go down in 12 hours or no? Or will there be an alarm or no? So we have two different categories here. We have alarm or no alarm. There's nothing in between, it's 1 or 0. So this means we have a classification problem. We want to classify if there will be an alarm in 12 hours or if there will not be an alarm in 12 hours. That is it's quite a simple case because classifications are quite simple. They're just few classes that we need to predict. And this is a binary classification problem because we have just 1 or 0. So that is what we want to predict. So we have all these KPI, these performance counters, and how do we go about doing this? So our labels here are alarm, no alarm. Pretty simple. And this is a classification problem, and input data is our performance counter from our Nokia base stations. The data points we had in this project was this kind of structure. We had 3 weeks of data in this project. We didn't have more. We would like to have more, but we just didn't, and we had to deal with that. 395 performance counters were selected based on experts that know that, okay, you should maybe look at these counters because they might do something. We have many more counters than 395, but we didn't take them all because it's like many thousands. We have a sample rate of 1 hour. That is quite standard. So every hour we have a measurement. So we have a time series starting from the start date, 1 hour sampling until the end of the 3 weeks. And the counters were these kind of things like channel quality, random access channel, these kind of hard handover, throughput, radio interference. Doesn't really matter what they are to you, but they were selected based on experts in the radio side of Elisa. And also, of course, the alarm data. So this is how the data structure looks like. It's a simple two-dimensional database with PM counters along the columns, and then we have the alarm. So we have the KPIs, and then if there was an alarm or no alarm, 1 or 0. Pretty simple. So, as I said, in the industry, we have a lot of data, but a lot of that data is not very, very nice. And what I mean with that is that if you just take this database that I pointed on and throw that into some machine learning algorithm, it won't learn much because it's not made in that way because it contains a lot of misleading things, let's say. First thing is that usually in almost all of these base stations there is no alarm because usually the hardware works, right? So in most of the cases we have just zeros, and in some base stations we have alarms. So now if you start to learn this thing on the whole data set, we will be very, very good at predicting a 0 because we have almost only zeros. But to predict that one alarm at some point in some week, it's almost impossible to do because the data is so imbalanced. It's so many zeros that you cannot handle that. So what we did was to get rid of all base stations that didn't have alarms because it's easy to learn how to predict a 0. So we just get rid of them and just keep the ones that have an alarm. Okay, then it's a little bit more balanced. We have, of course, to normalize the data that you probably know how it works. But still, even though we get rid of all that those base stations without an alarm, it is still like a 3-week span with a 1-hour sampling rate and maybe one alarm at some point. So still there's like almost only zeros, which means that you need a precision of like 99.999% in the model to kind of predict the alarm. So we need to do some oversampling on that data to kind of to help us, to help the learning algorithm. We need to expose the alarms a bit more. So what do? We have this situation here. Here's the time axis. Here we have 2 alarms that were registered. Now we want to, instead of predicting exactly when the alarm will come, we will instead predict only if it will come within 12 hours. So we make the prediction a little bit less precise, but the learning will be easier to do. So what we did was to extend the ones in a 12-hour window before every alarm. So we introduce more ones before that alarm comes, because before the alarm comes, maybe the KPIs look a little bit weird and they kind of have the trend that it's like something weird is going on. So we convert these zeros to ones, doing the oversampling. Yep. One more thing was to ignore post-alarm data. This is something that you won't think of maybe at the first step, but after the alarm comes, after the base station breakdowns, the KPIs are like weirding out. They are like, oh no, I don't know what's going on. They just have weird values, right? Because something is broken, so they can just show weird results. So after the alarm, we had to cut away a window of data because it was just nonsense. That's a very practical thing that has to be done based on this real use case. Okay, but then we made a training on this data. I cannot show all of the details because it's behind lock and key, but we are using Python. We use Python for everything mostly in Elisa, so learn Python, that's a good thing to do. Have Oracle database. Here we actually use a random forest method, so no neural network, no complicated things. Start simple. It's usually better to do that. Because if you can get away with a simple algorithm, you save a lot of time. You don't want to do big LSTMs right away because maybe it works with random forest. And if you have this time to market that you need to get this done in 3 weeks, go simple. Start with simple things. So we start with random forest. The training time on a local laptop is less than 1 hour, so it's kind of very manageable to do this. So here we have some results from a real test case in the Elisa network. Here we predict an antenna line device failure. The blue line is a real alarm, and the red bar is a prediction of 1. And if we have many predictions of 1 after each other, the red will become a stronger red. So you see here is some more red, and then after the alarm comes, the red kind of fades away because after the alarm comes, it looks like an alarmish situation after that one. Other alarms might be more difficult to predict, like a failure in optical interface. That is very difficult to predict. So here you see it is very uncertain when the alarm comes. So sometimes it works very well, sometimes it doesn't work so good. That is just how it is. But we did this training and we deployed this method in the Elisa automation network. So we have like this map of Finland, and we can kind of get this pin when the base station is about to fail. So an automation engineer can kind of go and look, okay, now something is going on here. Click there, what is the alarm that is going to come? Maybe dispatch a service unit if that is needed. So this is the summary of our alarm prediction. We actually have a paper on that one as well, presented last year in I don't know, it was some kind of signal processing conference. I never remember the name of those conferences. Okay, but lessons learned from that one was that the importance of oversampling when you don't have enough data that will give you the thing you want to learn. We have so few alarms, so we need to kind of expand on that data to kind of expose it to the algorithm to make it more easy to predict. Also ignore the post-alarm data, and I would say simple methods like the random forest works pretty well in some cases. Start with a simple method if you are not sure what to use. If you find out that that method really doesn't give you what you want, you can go more complex, but sometimes random forest is good enough. And you really want to have long enough time series, because that is how the algorithm learns. Okay, let's look at a second one. So Elisa doesn't just make our own kind of automation and our own use case. We also want to sell our software to other operators. So we have operators abroad that provide 4G to their customers, and Elisa also sells kind of, let's say, optimization software to make their network more optimal. So with that, we want to kind of do some capacity planning for our customers. And we want to, for example, predict in the customer network, like, okay, in 1 year we will have so and so many more users and so much more data volume. What will the user throughput be then? And if you don't do anything, you're going to have customers complaining because it's too much data volume. But if you buy our software, you will have better throughput and you will have less customers complaining, something like that. So this is what we want to show to the customer in other companies. So in this use case, we got a data sample from our customer. They give us the data and say, okay, do some analysis on this data and show what you can provide us. Here we want to predict user throughput, which means the throughput you have when you connect your phone to the internet. And that is the thing you want to have more than a certain limit, because when it goes below a certain limit, then web pages start to lag and you don't like it anymore. So we want to predict the user throughput for a cell. Here we got 12 PM counters, only 12. We have a 1 month data with a 30-minute data sample. This data was showing users, volume utilization, and we want to predict user throughput. So this is kind of a simple example again. The data set looks the same. We have the PM counters in the columns, the time like this, and then you want to predict one column, let's say the green one here. I think this is a quite typical machine learning case, that you have some columns and you want to predict what is the next one. So we start really, really simple, because if we are fine with simple, then that's what we're going to go with. We are not going to go extremely complicated unless we really have to, because that saves a lot of time. So we want to predict the user throughput based on the number of users connected to that base station. And if there are too many users connected to the same base stations, they need to share all the bandwidth. And if there are too many, of course, the bandwidth will be lower. Right. So first attempt, 2D curve fitting. This is not even machine learning. This is just simple mathematics, right? Curve fitting. We use, again, Python. This toolkit sklearn, that is quite helpful. Maybe you know that one. It is very simple to use. That is the one we have been using. We have a SQLite database and curve fit function from sklearn. Simple as that. This takes 5 minutes on the local laptop. So if this works, it is great for us, because then we get away with very little work. So what do we have here? We get a scatter plot of the user throughput and the number of users in an example of a base station cell. So what does it show? So the less users we have, the more user throughput. Makes sense. It's a good correlation. And we can easily make a model with a simple curve fitting function that can predict, okay, in the future, if you have so many users, then the user throughput will be so low that you can predict. So we give this to the customer and they look at it and they say, okay, this is good, but we actually don't want to predict users, because almost everyone has a mobile phone right now. We're not expecting to get so much more connections, right? So they say, can you instead predict what happens when the data volume increases? Because in 1 year, people will start to watch 4K on their mobile phone. The data volume will be like really big. So that is the thing that they want to predict, not the users. So we go back to the lab and, okay, let's try the same thing, but we just switch users for volume and see what happens. And that's what happened. It's a mess, you see. There's no correlation, almost no correlation, between user throughput and volume. And why? Because either you can have a lot of users using the internet and their combined volume makes a high volume, or you can have like one guy in the middle of the night downloading some torrent or something and use almost all of the bandwidth, right? So you have like few users, but the same volume. So there's no correlation. That is the problem here. So we cannot make a good model like this. This method is too simple. We don't capture everything that we want to have. So we start, looking at what can we try next? What is the next step we want to do? So let's try a feed-forward network. So now we start to go into the machine learning thing. Like, we have to do that because we cannot capture this thing that we want with the simple tool. So we train a feed-forward network, which on a high level works like you have your input utilization and volume, and based on that, you predict what is the user throughput. So you train with that one, and that one will give us that one. That one and that one will give us that one. Go through all the table like this. So that is the problem of regression that you want to predict. You don't want to predict a class. You want to predict, let's say, a floating point number based on other floating point number or integer numbers. So we use Python. Keras is the thing we used here. Maybe you know Keras. TensorFlow, which is the backend, and SQLite is the thing we also use a lot. It's very good to know SQL in general, and we create this model in 20 minutes, something like this, on a laptop. So it's still fine, still 20 minutes. It's more than 5 minutes. It takes more programming to do this, but it's okay. It's still okay. We do the prediction now. We take the real data that hasn't been trained in the model, throw it to the trained model and see what output we get. So the blue thing is the real data, the red curve is the prediction, and this is time, and this is user throughput. So by using more input parameters than just volume, we can get a better learning of the user throughput. And this was done with a neural network. We also tried this with the LSTM neural network with a time series prediction, way slower and a little bit better. So then it's up to the people in the group to kind of determine which way you want to go. In this case, this was the better case because it is faster to get working. And even though it's not super exact, you see here it's a bit off. It's still okay in this case. The lessons learned from this thing was that start simple and go upwards. If it's okay with simple, stop there, and that's okay. Usually in the academia, you don't want to do simple. You want to do all the most advanced things because you have read on the internet about some really cool method that you want to use because it's like has everything. But you don't need to do that. In the industry, you shouldn't start with the most complex things. Start simple. A simple check is to see that just if there is any correlation. If you have some correlation between two variables, you can do really just a curve fitting, and that's fine. One more. And this is the most complex one that we have done. Or I don't know that we have done, but in this lecture at least. So this case is about balancing users between different cells in a base station. And we have this kind of a big picture that we have the radio access network in the field giving us data in form of performance counters. Those counters we use to process and give us the algorithms, and then we can actually go back and change things into the network. We can apply settings to the base station so they behave differently depending on how we want to control them. The challenges here is that the mobile data increase is quite high. There's going to be more and more data volume, and traditionally we have actually been doing, or everyone has been doing, manual optimization. So in the past, when the GSM and 3G era, we had actually a person sitting and looking on 20 monitors to see if there's something that can be optimized, and it has to be like really a domain expert to see that, okay, something is weird here, maybe we can change these things, really by a person. And of course we cannot have that anymore because it should be a computer doing that automation. So now we are somewhere here, so the manual automation is of course declining, and the computer-based automation is like going up. And in the 5G we're going to probably have like only computer-based automation. In the current form, we have been doing automation with the simple if-then-else statements. So that is what has been used, and it works, but we can do better. We can do better than that. Our case here is based on a sector. That is a new word. A sector is a part of a base station where the cells have the same bearing. What does it mean? It's a cell and that cell has the same kind of, the beam is kind of directed in the same direction. That is a sector. So we have different frequency bands pointing in the same direction, 800, 1800, 2600 megahertz bands. And the thing here is that the users can jump between these bands. The 800 band kind of covers the furthest away, users furthest away, but it has also the lowest bandwidth. So if a user is like here, that user should probably not be on the 800 megahertz band because it could be moved up to the higher bandwidth. So that is a sector. Usually a sector contains 3 cells, and these cells are controlled by a threshold value. A threshold value can tell what should the signal quality be before the user moves up to the next band. So if you select this threshold value, you can control how many users should be in this band, and in this band. And you want to have kind of a even balance. You don't want to move everyone here because then that gets overloaded. You want to have a good balance, then everyone has a good bandwidth. And this has been done with these if-then-else statements in the past. So the problem here is that when should we migrate a user? How should the network conditions look like when we migrate the users? And that is based on these threshold values. So what value should we have on these threshold values such that the best possible balance is achieved? Again, we use the same performance counters that we did in the past alarm detection case, but of course we didn't use the alarm counters here, only the other counters. These are the same ones. We have a 1-month data dump with 1 hour sampling frequency. This is something like 30 gigabytes of data, so it's manageable on a laptop, but it starts to be a little bit too big, especially if you have a SSD drive like I have. It starts to be a little bit awkward to have that. But it's still manageable. We don't need a cluster for this. In this case, we noticed the importance of exposing the relations in the data. So what do I mean by that? One cell looks like this. So here is time, here is magnitude, and here are all the 395 variables plotted in a 2D graph. So it's just, you can't see anything because it's too much data. It's like crazy. That is one cell. If you start to train the network to predict the best performance in a single cell, it doesn't work very well. And why? Because if I am now in the 800 megahertz band and I have too many users and I want to migrate away some users, then I know that I will get better. But if I'm in the 1800 megahertz band, if I know that the guy next to me is going to migrate away users, I know that there are users incoming here. And that relation is not known if you just train on cell level data. There's no way to know that. And also, if you are in the 2600 band, if we know that 1800 band is migrating away users, we know that there's going to be users incoming, and I need to prepare for this thing. So how can we expose that thing? There's no data in doing that. So what we need to do is to get all three cells, the data frames for all three cells, and just merge them together into one big one. So we merge the three cells together into a 1185 variable big data frame. So now this relation is in there because you see that that one was migrating away users. As a consequence, that one got the users, and as a consequence, that might migrate away some of the users that were coming. So we really need to kind of think about how this thing works in practice and take the data and actually make our data frames so that it will actually learn something when we train the model. We use Python here, we use Oracle, we use SQLite, we use time series data, and here we use TensorFlow with LSTM, and this is a crazy one. If you have used LSTM on a lot of data, you know that this is heavy. It's a heavy thing. It takes a lot of time. To train this on my laptop takes like a week or something. So now it starts to be, you don't want to use LSTM unless you have to. I need to put this on a GPU, otherwise it's going to take a week. If I put it on a GPU, it takes 1 day, and it's still quite much. But we had to do LSTM here because we didn't capture the kind of time series pattern, the kind of the trend that was going on without that thing. But don't use LSTM unless you have to, because it's crazy heavy. So what do we optimize here now? We have these two threshold variables that determines how the users migrate between cells. And we get the performance for each of that cell. Now what we want to do is to maximize the combined performance for all three cells. We don't want anyone to be unhappy, so maximize that one. And that we can do by predicting the throughput and selecting different configuration variables. We have some simulation results from a Turku sample. Well, the blue one is the real data and the red one is the best configuration, that we can show that our configuration makes so and so much better. This is maybe not so interesting. The more interesting thing here is that we had to look at exposing the relations between the data. That was kind of the key here to get anything done. And we have to use LSTM for this use case, but yeah, it takes a lot of time, and you need at least a GPU if you have a lot of data. If you have 30 gigabytes of data, it starts to be heavy. Okay, what did we learn? What did we learn here? We had 3 different use cases here that I showed you. The first one was the alarm prediction, which was a classification problem. We classified the prediction as alarm or no alarm. Here we had to oversample the data. We had to bring in more data to kind of really expose what we were learning. In the other model, we had a variable user throughput, a floating point variable, basically, that we want to learn. And here we can point out to check the correlation between the data. If you can find easy correlation between data, you might get away with very simple methods like curve fitting. And in the time series data, we had to use LSTM to predict a future value based on past time series, and we had to expose the relations between different parts of the data in order to get this working. One interesting page maybe is that Elisa is currently hiring. We hire quite a lot of people now with this data science skills, with programming skills. So if you are on your final years, check out our vacancies. Usually want to have programming skills. You don't need to be an expert, but like know some Python. That is really good to know. Data science, machine learning, DevOps, and we also do thesis workers, internships, and these things. So if it's interesting, I can show you where you can apply for a job. And otherwise, thanks for your attention. Yes?
Yeah, I have a question which is less related to machine learning, but more related to education. So, imagine a case like flow testing. You have like tens of thousands of people gathering at the same place at the same time.
Yeah.
Like, I guess usually your calls are not meant for, let's say, 70,000 people gathering at the same time in one.
Correct.
And how do you manage those allocations? Do you bring supporting towers around, which is like, I don't know, portable towers or portable antennas around? Or do you use some kind of methods to allocate those users to different, I don't know, towers? Or how do you manage and try something?
Yeah, that question I don't know. That is a question more to the radio network side and not to the data science side so much. What I know is that we are like at least planning to kind of take that thing into account, because there are like gatherings all over Finland, mostly in Helsinki, that are really overcrowded. And if you can plan for a gathering, you can do some action. What that action is, that I don't know. That is more on the radio network side. So sorry, I cannot answer that question directly. Yes? Why did you go with oversampling? Well, we tried different combinations of different methods. That one seemed to work machine learning and kind of want to promote their products with machine learning. So, as a promoter, I would say Elisa is one of the better ones because we have a lot of resources. It's a big company. Finland is usually the first one to try out a new technology and kind of really on the edge. And since Elisa is the biggest in Finland, I would argue that Elisa has a good position to be really in the cutting edge of machine learning. And for example, we have a lot of these presentations on these RAN network conferences and all these things. So Elisa has a lot of things to promote and kind of show that we are actually doing this thing right now, and in the future we have a lot of ambitions. So that is kind of how it works.
Is there any company in the world where you turn to look when you want to see what's happening in the industry? Like, okay, this company, it's always making innovation in the different areas of this machine learning. Is there some companies like that?
Yeah, for example, O2 and Vodafone, I think they make it, of course they want press release and promote their own machine learning thing. And, they don't, of course, reveal any details, but based on the thing that they promote, we can look at, okay, is this the same thing as we have? Does this sound limited in any way? Are we better than that? And if we can be better, what should we do more? And so on. So it is kind of, it's a marketing thing that you need to show what you have and what you can sell. And it is not only about the technology, it's also about how to sell things. It's like a whole package. But so far Elisa has been actually one of the, we have been doing a 5G pilot, for example, that has been like a big promoter that Elisa is now on 5G. O2, I believe. Or O1, or what? O2, yes. Yeah. I don't know.
I have a question, two questions actually. One, you mentioned the databases that you are using. Why is it important? And the second thing is last study. So what was the result that you had from the last study? Examples you had. What was the result of that study?
The result of that study was to show that doing load balancing with AI gives better throughput than the traditional load balancing. So we have the blue curve was the kind of current user throughput, and the red one was kind of the simulated. This is not really the simulated. So you have model errors in these things, but to show that here are the potentials of that method. What was your first question?
You explained every case that what is the database that you use? Why you mentioned the database?
I mentioned it because you might be interested to hear what tools you use. Usually people are interested in that. So you use Oracle and you use SQL. So if you learn how SQL, it's very good to show that knowledge. Yeah. Yes, we are. The data collection is a big problem. It's not easy at all to do that, to make it into a structured way and collect those counters that we want. That is a big problem. We are currently working on an interface to more easily do that. Now we have been doing mostly manual work with like SQL queries. It's not really nice, but yes, the algorithms should scale up. Of course, you need maybe more memory, more hardware space. some methods like this random forest requires that you need to put all your data into the memory at once. So if you have 16 gigabytes, that's what you have. So that is a thing to look up for. If you know that you're going to have many gigabytes of data, you need to select a method that supports this kind of partial fitting of the model. That's a good one.
How do you manage this using privacy?
Yes, that is very important because we handle sensitive information and in the best case we would need to have our on-premise cluster. We don't have that, but the most sensitive thing is, for example, if you have user information that can be linked to an individual user. So if I have information that I know is connected to you personally, that thing is like super sensitive. So that pretty much has to be kept on-premise. Otherwise, if you have less sensitive information, maybe you can use Amazon or something like this if you have a good security configuration from their side. But if it is connected to a user, that's like super sensitive, and that is best to have on our own servers. Yeah.
One more question about data cleaning. What did you explain during the first tutorial, for example? Now we are very afraid with this data cleaning is also very, let's say, present for all of us as well.
Yes.
So, and you talk about the normalization.
Yeah.
So, when you have this data on the last phase, and you have three different cells, what kind of data cleaning and organized and normalization you have to do with that data?
With that, in that stage, the data was fine. So at that point, we didn't have to do anything more, but at first stage, we fetch the data from the database, and that's the raw format data. And that's very nasty data. You have missing time steps, you have non-values, you have some outliers that are just results from some track that's what's happening. So this is very use case specific, so you need to kind of actually write your pandas method to kind of check if that is something weird, then replace it with that thing. All those things have to be done step by step, so that in the end you have like a data frame that you can really consider as not having any weird things in it. But it is like 90% of the programming is just to go through that data, and it's always like that. We are working on a framework that you can actually more easily write your own cleaning plugins to, and kind of, I put my check for non-value plugin here, and I put check for valid length of time series here, and then you have your actions. So, but that is an important part, and it should be structured in a good way, because it's crazy how much you need to do that in that way. And I haven't seen any fast ways. You need to do the handwork and it's fast, but you have to do it.
One question after this.
Yeah. So that is a use case specific question, right? So if you have a time series and in the middle there's a gap because there wasn't any login data because of hardware fault or something. Now you need to decide in this use case what you want to do in that case. In my case, I just patch with zeros. Maybe you want to do interpolation. I don't know. So it depends on what the use case requires you to do. Maybe you can just ignore that thing. In my case, I can't ignore because I need to have the same length of each data frame. So they have to have the same dimension.